Okay, hey guys, it's Lorenzo again, and we're going to continue with the calculus topic. This is going to be the last video of this topic, and what we're going to cover is solids of revolution. So basically, what this subtopic has to do with is, let's say we had a curve like this, and we had, I don't know, this random line here. And let's say we spun that curve around the x-axis. So we're gonna get this just kind of, this is kind of just gonna spin around. This is gonna spin around the x-axis, all right? And that's gonna create a volume because it's three-dimensional, right? It's gonna spin around, and there's basically formulas to figure out what the volume of this would be. So basically the volume would be pi times the integral from a to b, so you kind of have to set limits for yourself, so yeah, a to b of f of x squared d of x. Yeah, so that's basically just know the formula, just solve it. It's the same as we did before, except that now it's the function squared and you're multiplying it by pi. Now, a different case, if we had this, and we had kind of like a function, so this is our f of x, and we spun it around the y-axis, right? So it's going to spin like, I don't know, like that, and it's going to spin this direction. We're going to again get a volume, but now it's going to be around the y-axis. So when it's around the y-axis, then it has a different formula. It's pi times a to b, but now it's not of f of x, but it's of x squared dy. So now you kind of solve for x, you plug that in. Instead of having a function, this is like a function of y. It's a function of y, not of x. Alright? So plug that in, and you're going to find the volume here. Alright? Now, so just know these formulas, you'll be able to do it then. Another interesting thing is if you have, I don't know, let's say another graph like this, and you have like a line and you had another curve, and this is f of x, this is g of x, and you want to find the volume of revolution that this kind of has when it spins around the x-axis, well then you say there's another equation for it. So it's pi from a to b of f of x squared minus g of x squared d of x. And I think that's very intuitive because you're kind of subtracting this volume, and you get from the total volume, you get the volume that is above here. So you always minus the smaller function, so the larger function, yeah, so you minus the smaller function from the larger function. Okay, so I'll do a little example. Let's do an interesting one. Like, let's do this function of x, 1 over x. Alright? So basically, the integral, let's begin with the integral. Let's just, basically, yeah, let me draw what 1 over this function looks like. It's kind of like this. So, if we find the integral, we find the area underneath. Alright? So let's find the integral from 1, which is somewhere like here, 1 to infinity of 1 over x dx. Alright? So this is going to be equal to the limit as b approaches infinity of 1 to b of x dx. So that's going to be equal to the limit as b approaches infinity oops, of ln x, right? Because that's the integral over x from a to b, which is ln b, remember from the last video, minus ln 0. So that's basically ln infinity minus oh, sorry, this is a 1. So this is 1. ln of 1 is 0. So it's going to cancel out. And ln of infinity is infinity. So what does that mean? The area underneath is infinite, continues forever. Doesn't stop. But what if we found the volume of revolution? So if we found, instead we use this formula, that one, the volume is going to be equal to pi times 1 to infinity of x minus 2, right? Because 1 over x squared is 1 over x squared, which is x to the power minus 2, dx. So therefore the volume is going to be equal to pi limit b approaches infinity 1 to b x minus 2 dx. Okay, so then v is going to be equal to pi times x minus 1 minus, from 1 to b, this is going to be equal to pi times pi of or 1 over b plus 1 over 1, because you get negative 1 over 1, negative 1 over 1, because there's, remember, if you have to find the integral, so it's going to be negative, so it's going to be positive. So 1 over b, as these limits should really be all over here. So 1 over infinity is going to give us 0. So then there's just going to be the 1 left. So this is going to be equal to pi. So strangely enough, we have found that the area of the integral itself continues forever, but there's a finite volume, which is kind of a paradox if you think about it. So yeah, that was an interesting example. That's it. We're done with the calculus.